time? Cool. What is time? We use it every day. But have you ever stopped and thought about how we measure time? Jocelyn, give me an example of how we use time every day.
To organize our calendars.
Cool.
And be in the right place at the right time.
Awesome. And why is that important to us?
Because we need to organize things to have social interaction with people.
All right, solid answer. So if we want to figure out what time is, then we should go all the way back to the foundations of where we are in the world, correct? And how did we all start out from, and how everything pertains to each other. And now, Ket's group will inform you on how the Earth moves and as well as everything around it.
Yeah, good morning everyone. So our group presentation is focused on the motion of the Earth. So before we will try to touch different ideas on this topic, but before we jump into the presentation, we will have simple interactive, which is called Kahoot. And I think everyone is logged in already, right? So okay, let's start the game. So you have 20 seconds to answer the question, and the question is, what did the Big Bang take place? When did the Big Bang take place?
Alright, yeah, so the answer is 13.8 billion years ago. And we're going to start our presentation. And the Big Bang, so how the universe came to be. So starting off with the Big Bang theory, it's the leading explanation for how the universe came to be. So the universe started out as a small singularity, and then eventually over time, over the course of 13.8 billion years, it started inflating, and it's continually inflating. So as we know now, the universe is expanding constantly. In the beginning, the universe was very hot. It was about 10 billion degrees Fahrenheit. So if you take into consideration that our sun is 10,000 degrees Fahrenheit, you'd have to multiply our sun 1,000,000 times just to equal the amount of the universe, the temperature of the universe. And in the beginning of the universe, there were particles, important particles, such as electrons, neutrons, and protons. And then they also had photons of light that scattered around constantly. Now after the Big Bang, about 380,000 years afterwards, the electrons and protons slowly started combining to form hydrogen. And we now know hydrogen is the most abundant element in our universe. And it also created the cosmic microwave background, which some people like to call the afterglow of the Big Bang. And I'm going to bring this over to Edgar for galaxies.
Thank you, Tim. Galaxies, a ton of them. We live in a planet called Earth, in a solar system called the solar system, in a galaxy called the Milky Way, which is part of 100 billion galaxies that are in this universe. What is a galaxy? A galaxy is a group of gases, dust, and millions or billions of stars that are around the space. And how the galaxy sticks together? It sticks together thanks to something called the gravity. The galaxies at this time are okay, so there is some galaxies too close to each other, and we are one of them. We are close to the galaxy Andromeda, and scientists say that in 5 billion years, we're going to hit this galaxy, and even if it happens tomorrow, you won't even feel it. Because the galaxies are so expanded that even if the galaxies touch each other, there is a very small percentage that the planets will collapse because of this reason, because the planets are too separated from each other. So we have three types of galaxies. We have a spiral galaxy, an elliptical galaxy, and an irregular galaxy that it basically has no form. So I'm going to go ahead with a solar system with Berkeley.
Thanks. So before the idea of the solar system, there was asteroids which believed to introduced before 4.5 billion years ago, when the cloud of gas which is called solar nebula, and which is collapsed, they formed the sun and the planets around it. So asteroids are like a rocky world which revolves around the sun, and they are very small, so they don't count as a planet, or they don't call as planets. And these asteroids are like there are millions in the universe, and they exist in different different size. So let's jump to the solar system. What's the solar system? So the solar system is made up of the sun and everything orbits around it, like planets, moons, asteroids, comets, and meteoroids. So let's focus on the planet system. As you see in the picture here, every planet orbits the sun on their own axis. So what do you think the reason is? What do you think the solar system keeps together all these planets on their own axis? What do you think the reason is?
Polarity.
It's gravity. So gravity, the sun gravity pulls everything towards the sun, and that changes the straight line of the direction to the curve. So in that way, all the planets are moving around their orbit or their axis around the sun. So that's the reason. And the Earth is here, the third planet in the solar system. So yeah, and there's according to the solar system, and there are different reasons actually to where existing in the Earth. There's gravity and there's different things, but we focus on solar system. According to solar system, we are safe in Earth. And so you are one of the billions in the Earth. So Earth orbits around the sun, and the sun is one star among the billions of galaxies, Milky Way galaxies, and our Milky Way galaxy is one of among billions of galaxies in the universe. So this is the solar system. We'll talk more about the movement later, and now I'll hand it to Amanis to talk about the Earth's orbit.
Thank you, Bernard. Good morning, ladies and gentlemen. I'll be explaining about the Earth's orbit. So that's an interesting topic. We have the Earth moves, motion. Motion is something we see every day. People, cars, airplanes, ships, always moving. So does planet Earth. So when I want to talk about motion, I want to start by axis. What's an axis? If you can see the picture up here. Axis is the imaginary line that starts from the South Pole to the North Pole, or North Pole to the South Pole, that's drawn by the center of the Earth. If you can see, even actually the globe, we have an axis, that's the imaginary line. And the Earth is always tilted at 23.5 degrees. And I'll get to that later, it's very, very important. Now I want to move out to the types of motions the Earth has. We have rotation, revolution, and also precession. First I want to talk about revolution. If you can see the picture up here, revolution is the Earth's movement around the sun, which is about 365 days, which we call a year. You might be thinking, how about a day? A day is created by Earth rotation, which means the Earth rotates in its own axis, like I've seen, like I told before. It takes 23 hours, 56 minutes, and 4 seconds for an Earth to finish its own orbit, which is a day, which we call a day. And the Earth concludes this with about 1,000 miles per hour, which is so fast. Going on to the next slide, I'll be talking about precession and tilt. Precession is a motion that's caused by the gravity pull from the sun and the moon. Show the light dome actually. So precession is a movement, it's a wobble. The Earth wobbles which we call precessive in a circular way. So we don't really feel it, but that's one actually the best reasons why we have 4 seasons on Earth. Because the North Pole won't be facing the sun. For example, the Earth wobbles slowly for about 26,000 years, so that the North Pole won't always be facing the sun. That's why we see difference in climate and seasons. And last thing I want to say is a tilt. A tilt is one of the most important things that scientists have been talking for like years now. And I want to ask you a question, and I want to conclude my presentation by a question. What if there was no tilt? What do you think would have happened? Do you think humans would have survived? Do you think we could have survived? Do you think if the Earth was tilted 90 degrees, not 23.5 degrees, do you think we could make it? I'm going to leave the answer for you, but I have only one suggestion. If the Earth was not tilted, or if it was tilted 90 degrees, Seattle wouldn't be here today. Thank you. I'm going to pass it to Dan.
Alright, so next and the last slide is our solar system's movement. And we're going to talk a little about the vortex motion. So our solar system is headed towards the Great Attractor. Now what the Great Attractor is it's an anomaly in the intergalactic space that is in our galactic supercluster. Now what a supercluster is a bunch of galaxies, neighboring galaxies together. So about 100,000 galaxies for our supercluster, including the Milky Way. And in the middle, there's the Great Attractor. And everything in that supercluster is going towards the Great Attractor. Now, our solar system is headed in the direction of the constellation of Leo and Virgo. And in here, you can see the picture. It shows how our solar system is moving. So our sun is moving like a comet in a straight forward line towards the Great Attractor. And the planets are being dragged along with the sun in a vortex motion. This would be a GIF, but Freddy doesn't do GIF. So it's moving in a vortex motion. Next, go to the next slide. Now this ties into the Fibonacci sequence. So vortex is important because of the Fibonacci sequence. Now the Fibonacci sequence is this diagram right here, and inside you see this Fibonacci spiral. You can see that? And basically the spiral explains a lot of things in our life. So life is a vortex. There's a lot of things in nature that mimic the spiral, such as a ram's horn, or nautical shells, or even certain types of plants. And more specifically, our own solar system, our own galaxy. So our galaxy, the Milky Way, is a spiral galaxy, and as you can see, it ties along greatly with the Fibonacci sequence. And the Fibonacci sequence is a mathematical formula, but I don't want to get into that too much because Rick is going to go over that with us next week. And that concludes our presentation.
Questions?
Awesome! Woo! That
Questions?
was a lot of information to take in. How many of you guys feel dizzy because that was a lot of information to take in? Oh, sorry. Yeah. It's quite strange how fast the Earth moves and we're constantly moving, but we don't feel dizzy. Have you ever thought about that? That's cool. Thank you for saving us the headache. Science. Well, now that we know what the playing field is like, thank you for presenting. Now that we know what the playing field is like and where the Earth is in consideration to everything else, let's move it back and take it back to Earth where we are and why that's important to us and how we figure this out. And so I'll call upon Anna.
Wait.